the cavity modes. For that we consider an active medium which is placed between plane mirrors M1 and M2 with mirror M1 at Z equals 0 and mirror M2 at Z equals L. The electromagnetic radiation in the laser cavity can be expressed by Maxwell's equations. The first equation is del cross E equals minus dou B by dou T. Second one, del cross H equals J plus dou D by dou T. Third one, del dot D equals rho. And fourth one, del dot B equals 0. Here rho represents the charge density, J is the current density, E is the electric field, D is the electric displacement, B is the magnetic induction, and H is the magnetic field. Inside the cavity we can assume rho equals 0, B equals mu 0 H, D equals epsilon 0 E plus P, and J equals sigma E. Here P is the polarization, sigma is the conductivity, epsilon 0 and mu 0 are the dielectric permittivity and magnetic permeability of a free space. Here the conductivity terms leads to the medium being lossy, and which implies the attenuation of the field. The other losses like that due to diffraction, then finite transmission at the mirrors are taken into account in sigma. From equation 1 we have del cross E equals minus dou B by dou T. Now we can write del cross E equals del cross minus dou B by dou T. That is del cross E equals minus mu 0 dou by dou T of del cross H using equation 6. Now we can write del cross E equals minus mu 0 dou by dou T of J plus dou D by dou T. This is from substituting the value of del cross H from equation 2. Now we can write del cross E equals minus mu 0 dou J by dou T plus dou square D by dou T square. That is del cross E equals minus mu 0 dou J by dou T minus mu 0 dou square D by dou T square. So we can write del cross E equals minus mu 0 into dou by dou T of, instead of J substitute sigma E, minus mu 0 dou square by dou T square, and instead of D substitute epsilon 0 E plus P. That is from equation 7. Equation 7 and 8. And on further simplification we can write the expression as del cross E equals minus mu 0 sigma dou E by dou T minus mu 0 epsilon 0 dou square E by dou T square minus mu 0 dou square P by dou T square. That is del cross E plus mu 0 sigma dou E by dou T plus epsilon 0 mu 0 dou square E by dou T square equals minus mu 0 dou square P by dou T square. The losses are small, that is sigma nearly equal to 0, and the medium to be dilute, that is P nearly equal to 0. Therefore the second term on LHS and the term on RHS vanishes. So equation 10 can be rearranged as del cross E plus epsilon 0 mu 0 dou square E by dou T square equals 0. So inside the cavity rho equals 0, and then by equation 3 we can write del dot D equals 0 or del dot epsilon 0 E plus P equals 0 using equation 7. Since P is small, we can write del dot epsilon 0 E equals 0, that is epsilon 0 into del dot E equals 0. Also we can write del cross E equals minus del square E plus del dot E. And since del dot E equals 0, we can write del cross E equals minus del square E. That is del cross E, or we can write del cross E equals minus dou square E by dou x square plus dou square E by dou y square plus dou square E by dou z square. But the intensity variation in the directions transverse to the laser axis is small in distance, approximately equal to lambda. Therefore, we can write dou square E by dou x square equals 0 and dou square E by dou y square equals 0. Equation 13 can be written as del cross E equals minus dou square E by dou z square. So from equation 11 we can write del cross E equals minus epsilon 0 mu 0 dou square E by dou t square. Comparing this equation and equation number 14, we can write minus dou square E by dou z square equals minus epsilon 0 mu 0 dou square E by dou t square. Square E by dou z square equals epsilon 0 mu 0 dou square E by dou t square 1 by c square, and on substituting that value we get dou square E by dou z square equals 1 by c square dou square E by dou t square by the method of separation of variables. Here LHS is a function of Z and RHS is a function of t. So we can write E of ZT equals Z of Z T of t. Differentiating equation 17 with respect to Z twice, square E by dou Z square equals T of t dou square Z by dou Z square. Again, differentiating equation 17 twice with respect to t gives dou square E by dou t square equals Z of Z dou square t by dou t square. Substituting these values in equation 16 gives, that is t dou square Z by dou Z square equals 1 by c square Z dou square t by dou t square. Again, dividing throughout by Z of t gives equation in this form, that is 1 by Z dou square Z by dou Z square equals 1 by c square into 1 by t dou square t by dou t square. Let it be equal to minus k square. So first consider 1 by Z dou square Z by dou Z square equals minus k square. That is dou square Z by dou Z square equals minus zk square, or dou square Z by dou Z square equals minus k square Z. This actually represents the expression for a simple harmonic motion, and its solution is obtained as Z of Z equals a sin k Z plus theta. Here the quantity k corresponds to the wave number. At the cavity ends, that is at Z equals 0 and Z equals L, the field vanishes. Hence, Z of Z will vanish. Thus we can write, that is at Z equals 0, capital Z equals 0. Z, that is, it is equal to 0. 0 equals, instead of A, we substitute another constant D into sine k into 0 plus theta. Or we can write 0 equals d sine theta. Similarly, at Z equals L, we can write Z of Z equals d sine KL, or 0 equals d sine KL. And this is possible when k equals n pi by L, where n equals 1, 2, 3, etc. And the corresponding time dependence can be found out by considering, and the corresponding time dependence can be found out by considering the equation. By some simplification, we can write 1 by c square into 1 by t dou square t by dou t square equals minus k square that is dou square t by dou t square equals minus k square c square t. The corresponding time dependence can be found out by considering the equation which we have already written, which is of the form 1 by z d square z by d z square equals 1 by c square 1 by d t square equals minus k square. On simplification, we can write 1 by c square into 1 by t. This 1 by c square into 1 by t d square t by dt square equals minus k square. Therefore, we can write d square t by dt square equals minus k square c square t minus k square t square c, or d square t by dt square equals minus of k square c square t. Therefore, we can write t equals b cos k c t plus 5, but k equals n pi by l. So we can write t equals b cos n pi by l c t plus 5. Thus the corresponding time dependence will be of the form of cos omega n t. Here omega n equals k n c, that is n pi by l into c. We have already written that z of z t equals z of z t of t. This equation becomes d sin k z plus theta into b cos n by c by l into t plus 5. Thus we can write EZT equals sigma n a n z into cos omega n t. Let dB equals an Here we have taken phi equals 0 and theta equals 0, and let dB equals a. So we can write E0 of t equals sigma n a n cos omega t sin k n z. Suppose that in equation 10 sigma is not equal to 0. That is, we include the term describing the losses. Then we can write equation 10 in the form del cross E plus mu 0 sigma dou E by dou t plus epsilon 0 mu 0 dou square E by dou t square equals 0. But we can write del cross E equals minus dou square E by dou z square. So we can write minus dou square E by dou z square plus mu 0 sigma dou E by dou t plus epsilon 0 mu 0 dou square E by dou t square equals 0. But we know that mu 0 epsilon 0 equals 1 by c square. Now hereafter we can write plus mu 0 sigma dou E by dou T plus 1 by C square dou square E by dou T square equals 0. That is dou square E by dou Z square minus mu 0 sigma dou E by dou T equals 1 by C square dou square E by dou T square. Now if we assume the same spatial dependence, that is nearly equal to sin k n z, and the time dependence is to be of the form exponential I a n t, then we get a n square minus mu 0 sigma c square I a n minus omega square n equals 0. And on further simplification we get a n equals 1 by 2 I mu 0 sigma c square plus or minus mu 0 sigma square c raised to 4 plus 4 omega n square raised to 1 by 2. A n nearly equal to plus or minus omega n plus I sigma by 2 epsilon 0. Thus the time dependence is of the form exponential minus sigma by 2 epsilon 0 t into e raised to plus or minus I omega n t. Here the first term represents the attenuation of the wave, and the attenuation coefficient does not depend on the mode number n, but in general there is a dependence on the mode number. We explicitly indicate by writing the time dependent factor, that is exponential minus omega n by 2q n t equals e raised to plus or minus I omega n t. But here qn is the qualitative factor, which is given as qn equals epsilon 0 by sigma omega n. Equation 23 becomes ez of t equals sigma n a n exponential minus omega n by 2q n t into cos omega n t sin k n z. And on simplification we get dou square e by dou z square minus mu 0 epsilon 0 dou e by dou t minus 1 by c square dou square e by dou t square equals mu 0 dou square p by dou t square. Here we assume that E to be of the form E equals 1 by 2 sigma n E n of t exponential minus I omega n t plus phi n t plus complex conjugate. Sin CC stands for complex conjugate. Then only E will be real. So we can say that E n of t and phi n of t are real slowly varying amplitude, and the phase omega n is the frequency of oscillation of the mode, which in general will be slightly different, which will be in general will be slightly different from omega n. So let us assume that P is of the form P equals 1 by 2 sigma n P n t is z exponential minus I omega n t plus phi n t plus complex conjugate. And from equation 32 we can calculate dou square E by dou z square, dou E by dou t, and dou square E by dou t square. Also we can calculate the value of dou square P by dou t square. Then on substitution in equation 30 and after rearrangement we get the equation as omega n square E n minus I sigma by epsilon 0 omega n E n minus 2I omega n dot minus 2I omega E n dot minus omega n phi n dot square E n equals omega n square by epsilon 0 p n of t. That is p n of t equals 2 by l integral 0 to l p n t z sin k z dz. Here we have neglected the terms involving E n double dot, phi n double dot, p n double dot, then E n dot, phi n dot, then sigma E n dot, then phi sigma then phi n dot, p n dot and p n dot. And also we can say that omega n will be close to capital omega n. Then we can write omega n square minus omega n plus phi n dot square minus phi n dot square nearly equal to 2 omega n equals to omega n minus phi n dot. Again, equating the real and imaginary part of both sides of equation 3, then we get phi n dot minus omega n of t equals minus 1 by 2 omega n epsilon 0 real part of Pn of t, and En dot t plus 1 by 2 omega n t dash n En of t equals minus omega n by 2 epsilon 0 imaginary part of Pn of t, where we have taken Qn dash equals epsilon 0 omega n by sigma. Here when Pn of equals 0 and omega n equals omega n, and En of t will decrease exponentially with time, it will be consistent with our earlier findings. In general, we can define the susceptibility chi through the mean. Now we can define the susceptibility chi through the equation Pn of t equals epsilon 0 chi n En of t. This is equal to epsilon 0 chi dash n plus I chi double dash n En of t. Here chi dash n and chi double dash n represent the real and imaginary part of xn respectively. Then we can write omega n plus phi n dot equals omega n minus 1 by 2 omega n chi n dash, and En dot equals minus 1 by 2 omega n by Qn dash En minus 1 by 2 omega n xn double dash En of t. Here the first term on the RHS represent the cavity losses, and the second term on the RHS represent the effect of the medium filling the cavity. Then if chi n double dash is positive, then the cavity medium adds to the losses, and when chi n double dash is negative, the second term leads to a gain. The second term leads to a gain. That is minus chi n double dash equals 1 by Qn dash. That is, if minus chi n double dash greater than 1 by Qn dash, then there will be a build-up of oscillation. If we neglect the term phi n, then the oscillation frequency differ from the passive cavity frequency by minus 1 by 2 omega n chi n dash, which is known as the pulling term. In order to understand the gain and pulling effects due to the cavity medium, we consider a plane wave propagating through the cavity medium. Here xn represents the electric susceptibility of the medium for the wave. Then the permittivity epsilon of the medium can be written as epsilon equals epsilon 0 plus epsilon 0 chi n. That is epsilon 0 into 1 plus chi n. And this shows that the complex refractive index of the cavity medium is sigma is epsilon by epsilon 0 raised to 1 by 2 equals 1 plus chi n raised to 1 by 2. That's nearly equal to 1 plus 1 by 2 chi n, or which can be written as 1 plus 1 by 2 chi n plus 1 by 2 chi n double dash. The propagation constant of the plane wave. becomes beta equals omega by c epsilon by epsilon 0 raised to 1 by 2, which is nearly equal to omega by c into 1 plus 1 by 2 chi n dash plus 1 by 2 I omega by c into chi n double dash, which can be written in this form: alpha plus I delta, where alpha equals omega by c into 1 plus 1 by 2 chi n dash and delta equals 1 by 2 omega by c chi n double dash. Thus we can say that a plane wave propagating along the z direction would have a z dependence, which is of the form e raised to I beta z equals e raised to I alpha x into e raised to minus delta x. Here we can see that the absence of component due to the laser transition chi n dash equals chi n double dash equals 0, and the plane wave which propagates through the medium undergo a phase shift per unit length of omega by c. Chi n double dash is negative when the beam is amplified as it propagates through the medium, and the response of the medium is stimulated by the field, and the applied field and the stimulated response are phase coherent.